All right, let's dive into one of the biggest, most mind-bending puzzles in all of modern science. It's a story about a single number, a number that's supposed to define our entire universe. The only problem? We can't seem to agree on what it is.
So, it all boils down to this one seemingly simple question. How fast is our universe expanding? For decades, astronomers thought they were getting closer and closer to nailing down the exact answer, a value that literally holds the key to the universe's age, its size, and its ultimate fate.
But here's where things get really weird. There's a huge problem. When we use our two most trusted, most precise methods to measure this expansion, they give us two different answers. And we're not talking about a small rounding error. Both sides are completely confident in their data, yet they just will not agree.
Okay, so let's look at the numbers. On one side, you've got measurements from the early universe, basically the afterglow of the Big Bang. That data gives us a speed of about 67 kilometers per second per megaparsec. And a megaparsec, by the way, is just a ridiculously big yardstick, about 3.3 million light-years. But when we measure stars and supernovae in the universe closer to us, the local universe, we get a value closer to 73. Now, that might not sound like a big difference, but in cosmology, that gap is a chasm. It's called the Hubble Tension, and it means our understanding of the baby universe just doesn't line up with the adult universe we see today.
And that's why this is such a big deal. This isn't just physicists arguing over details. This is a crack in the very foundation of our understanding of the cosmos. It's a huge clue that could be pointing to brand new physics, maybe unknown particles, or a story of the universe that is way, way stranger than any of us ever imagined.
So to really get a grip on this cosmic showdown, we've got to rewind the clock and see how we got here in the first place.
You know, for most of human history, we looked up at the stars and thought the universe was static, unchanging, eternal. But then, in the 1920s, an astronomer named Edwin Hubble made a shocking discovery. Pretty much every galaxy out there is moving away from us. The universe was actually getting bigger. Fast forward to the 60s, and we find the cosmic microwave background, the oldest light in the universe, a literal echo of the Big Bang. And today, with incredible tools like the Hubble and James Webb telescopes, we're peering deeper into space with more precision than ever before, sharpening this incredible picture of a dynamic, growing cosmos.
So how in the world do you measure something as vast as the universe? I mean, you can't exactly use a tape measure, right? Well, astronomers came up with a brilliant solution. They use things called standard candles. Think of them as cosmic lighthouses. If you know exactly how bright a lighthouse is supposed to be, you can figure out how far away it is just by seeing how dim it looks from your ship. Same idea, but with stars.
And from that idea, we build something called the cosmic distance ladder. Each step allows us to measure farther out. First, we use a technique called parallax for nearby stars. It's like holding your thumb out and watching it jump back and forth as you close one eye and then the other. We use those measurements to figure out the distance to a special kind of pulsing star called a Cepheid variable. Then we use those stars to calibrate the distances to our most powerful lighthouses of all, Type Is supernova. These are spectacular exploding stars so incredibly bright we can see them clear across the other side of the universe.
So, by the 1990s, armed with this amazing distance ladder, astronomers set out to measure exactly how much the universe's expansion was slowing down. I mean, it had to be, right? Gravity pulls everything together, so the expansion should be hitting the brakes. But what they found instead was one of the biggest plot twists in the history of science.
I love how Nobel laureate Sal Perlmutter described it. It just completely blew everyone's minds. The universe wasn't slowing down, not even close.
It was speeding up. Some invisible, mysterious force was out there acting like a cosmic anti-gravity, overpowering the pull of all the matter in the universe and pushing space itself apart faster and faster.
And the scale of this mystery is just staggering. When we do a cosmic census and tally up everything that exists, it turns out that all the ordinary stuff, you, me, the Earth, all the stars and galaxies, makes up only about 5% of the universe. The rest is, well, dark. About 27% is dark matter, and a mind-blowing 68% is this mysterious force that's driving the acceleration.
So, what do you do when you find a mysterious culprit? You give it a name. Scientists called this prime suspect dark energy. But you know, just giving it a spooky name doesn't explain what it actually is. So, in physics terms, dark energy is this hypothetical energy that has negative pressure. The best way to think about it is this.
Gravity is a pressure that pulls things together. Dark energy does the exact opposite. It's a pressure that pushes everything apart, like trying to force the same poles of two magnets together, but on the scale of the entire cosmos.
So what could it possibly be? Well, we've got two main suspects in the lineup. The first is the cosmological constant. It's an idea Albert Einstein actually came up with and then called his greatest blunder. It suggests that dark energy is just a fundamental property of empty space itself. It's constant, it's everywhere, and it never changes. The second theory is called quintessence, and it's a bit wilder. It suggests dark energy is a whole new type of energy field that can change over time. And if it gets stronger, it could lead to a crazy outcome called the Big Rip, where the fabric of space itself literally tears apart.
Now, here's the crucial point. While the cosmological constant actually fits our observations pretty well, there's a problem. Our best theories from quantum mechanics predict what the energy of empty space should be, and the prediction is catastrophically wrong. And I don't mean a little bit wrong. It's off by 120 orders of magnitude. That's a 1 followed by 120 zeros. It has been called, and this is not an exaggeration, the single worst prediction in the entire history of physics. It's a giant flashing red light telling us that our two great theories of the universe, general relativity and quantum mechanics, do not get along.
Okay, so this huge problem has led some scientists to ask a really radical, almost heretical question. What if the problem isn't some new, mysterious energy we can't find? What if the problem is that our basic assumptions about the shape of the universe are wrong?
A fascinating research paper asks this very question. What if we've been chasing a ghost this whole time? Instead of inventing a brand new force just to make our observations fit, what if we just tweaked the starting conditions, the geometry of the universe in our models?
See, our standard model of cosmology assumes the universe is basically the same everywhere, expanding uniformly. To make that model work with what we see, you have to add in dark energy. But this alternative idea proposes something totally different. Imagine our universe is like a bubble, an expanding sphere, but it's surrounded by a shell, another region with a different density. Well, the math shows that as our bubble universe expands, the interaction with that outer shell could naturally create the acceleration we see. No dark energy needed. It's just a consequence of the universe having a different shape.
And that leaves us right here, standing at a crossroads at the very heart of this cosmic mystery. Is the Hubble tension a smoking gun, pointing us toward a universe dominated by some bizarre, unknown energy we can't explain? Or is it a subtle clue, telling us that our most fundamental assumptions about the very shape of the cosmos have been wrong all along? Whatever the answer turns out to be, you can be sure it's going to change absolutely everything.